you now see how to analyze each refrigeration cycle component piece by piece by piece. Uh, Pretty straightforward. Using Chapter 4 material, so a little Chapter 6 material if you have compressor efficiency, Chapter 3 material looking up properties. Um, Now, what I'd like to do is give you some ideas about putting it all together, putting all these pieces together, and what might you be expected to do in terms of analyzing a refrigeration or heat pump cycle and system, and what kind of things might you be asked to find. So I guess I've called this vapor compression refrigeration cycle analysis, where you're going to be going through a process where you're analyzing the whole thing. You're going to refresh your memory with the sketch, of course. You now see how to analyze the compressor, the condenser, basic heat exchanger, the expansion valve, constant enthalpy throttling device, evaporator, basic heat exchanger. And by putting all those four open systems together, that gives you the ability to transfer heat from cold to hot. In the whole scheme of things, that's a relatively new technology in the history of the world. Transferring heat from cold to hot in a planful manner uh, is a pretty new concept, isn't it? You've gotten good at visualizing the process and the cycle on a TS diagram. You see that, you see the counterclockwise rotation. That's what immediately tells you that W dot net is definitely going to be a negative number. It takes power to transfer heat from cold to hot. Usually what's given when you're asked to do a refrigeration or heat pump cycle analysis, what's usually given to you? Well, one, of course, is that it's either going to be a refrigerator objective or a heat pump objective. Okay. You're generally going to be given the type of refrigerant that's going to enable you to know what tables do I need to go to in the back of the book or in property tables. Now, typically what's given is the desired heat transfer rate, or in other words, in my world, the energy sought. In other words, what's the objective heat transfer rate in terms of kilowatts or BTUs per hour, or even in the units of some strange units called a ton. A little bit more on that in a second. I'm seeing that, but this is an old traditional unit that still continues to be used in industry. Also, what's given are key pressures, operating pressures, some key temperatures, and the phases. In other words, saturated liquid or a saturated vapor at a certain point. But certainly pressures and temperatures are commonly given. Another thing that came in my mind also is certainly what would be given would be some information about the compressor that you're using. Is it a reversible and adiabatic compressor, or is it an adiabatic and irreversible compressor in which the compressor efficiency is known or given? So that also would be given. I didn't have that on my list. Now, usually what's needed, what's asked for in a traditional cycle analysis for refrigerators and heat pumps, traditionally, you're seeking to find the coefficient of performance, beta or gamma. You're also normally trying to find the mass flow rate of refrigerant needed to achieve that heat transfer objective. In other words, kilowatts or BTUs per hour or tons of cooling for a refrigerator, or kilowatts or BTUs per hour if it's a heat pump heating situation. Normally you're asked to find what kind of mass flow rate do I need for that? Okay. And also then finally, it's common to ask how much power is required to run the cycle. And that's purely going to be the compressor power, right? Because there's no power associated with that expansion valve, that irreversible expansion valve process. So usually that's what's needed: coefficient of performance, mass flow, and power required to run the compressor or cycle. A little bit about what's a ton of refrigeration. And so it has been very common to express air conditioner capacities in tons. I'm seeing less and less of that being given at Home Depot and Lowe's, but you still see it from time to time. Now, at the industrial level, we still see chillers quoted in terms of tons of cooling. So I want to communicate to you what's this thing behind this unit called a ton of refrigeration? What's all that about? And so this means the cooling effect is 12,000 BTUs per hour for each ton. A little more of that. That's what that means. That's what a ton of cooling is equivalent to 12,000 BTUs per hour heat transfer rate. So how did this come about? Well, it came about when refrigeration cycles, before air conditioning was invented, making ice was the first application of refrigeration cycles. So making ice, and people would buy ice and put them in what they called the ice boxes. There were no refrigerators. They were what they were called ice boxes. So they would buy ice by a cube, a huge block of ice. People would buy. Okay, and so the historical measure of making ice was the amount of heat removal needed to turn 1 ton of water into 1 ton of ice in one day, one 24-hour period. So that's where the term ton was invented. And so it's sort of a neat historical perspective back in the days, kind of like turn of the century, from 1900, turn of the century, when there was no air conditioning, and there were no refrigerators, but there certainly was a need to provide residential people with ice to keep their food cool. Okay, and so anyway, what's your conversion factor? Say enough of the history. Okay, so if you've looked at my videos, you see that I love multiplying things by unity, and that's what enables me to keep my unit straight. And so unity equals 12,000 BTUs per hour divided by 1 ton. That's an expression of unity. It could also be called a conversion factor. 12,000 BTUs per hour in 1 ton. Also, you can do the math and you can satisfy yourself that 3.52 kilowatts of cooling is equivalent to 1 ton of cooling. So there you go. You can take a screenshot of this. You can look this up on Google as well. So that's what a ton of cooling is all about. Where would you start when you're asked to do a full analysis of refrigeration cycle? You're going to start at the inlet of the compressor. That's the traditional place that you start, because typically in the given information, you're given information about the compressor inlet phase or state. Okay, and so typically P1 is given, and very typically we consider the compressor inlet to be saturated vapor, as shown here on my TS diagram. So normally we start saturated vapor going into the compressor. Well, what are you going to do? You're going to look up H1 and S1 immediately. So if you know P1 or T1, okay, it's a simple matter to go to your property tables, look up H1 and S1, write those down. The next thing you need to do is understand your compressor. What's given? Is the compressor given as reversible and adiabatic? In other words, keyword ideal. If you read the word ideal refrigeration cycle, that means the compressor is reversible and adiabatic. Otherwise, you're going to look for compressor efficiency given to you. And that's going to determine the way you analyze the compressor process. Okay, so you have a decision to make, don't you? But ultimately, you want to find the work, the little w of the compressor. W dot over M dot. You're looking for little w. Well, If you've got an isentropic reversible adiabatic compressor, the job is fairly easy. Okay. You for isentropic, you know that S2 equals S1, or in other words, 2I is S1. And then you're going to determine H2I, since you're going to know the pressure and you have the second independent property, you can look up H2I and then use the first law to determine the isentropic work WI. Use the first law. Find out it's a negative number. Now, it's a little more complex if you have a adiabatic and irreversible turbine, and that's where you're going to have to apply the compressor efficiency to determine the work actual, and then you're going to go back and back calculate H2 actual. So I've written a little note here on this slide. What's the bottom line? The bottom line is no matter which of these you have, you've got to calculate the work of the compressor, W dot over M dot, and you've also got to figure out what is H2. And the order in which you do that depends on whether you have an irreversible compressor or a reversible compressor. The next step is analyzing the condenser, and your job is to find little QH. Little QH. Well, let's see. You know that there's no work associated with the condenser, and so QH is going to be a positive number. I'm sorry, you're rejecting heat. In the condenser, you're rejecting heat. So as I've shown on my slide here, Q dot N is less than 0. You're rejecting heat. So Qn less than 0. It's first law, it's going to be H3 minus H2. You've already found H2. Typically, H3 is an easy lookup because typically the phase of state 3 is a saturated liquid. So if you know P3, H3 is an easy, simple lookup value. Next is you're sort of analyzing the expansion valve, but since we've gone through the nuts and bolts of the expansion valve, you remember all of the lecture about that, the throttling valve, no heat transfer, fully adiabatic, no work coming out, little W0. And so in the absence of changes in kinetic energy, it's constant enthalpy. H4 equals H3. That's statement of the first law. So that really makes life very easy for the expansion valve and ultimately going into the evaporator. So the evaporator process, your job is to find little QL, right? So little QL, here I've got it right. Little QL, that's going in. So little QL is a positive number, okay? You're going to apply the first law, of course, and see that it's H1 minus H4. First law of thermodynamics, open system, one inlet, one outlet, steady state, steady flow. QL, work is 0, equals H1 minus H4. And by golly, this is pretty easy, right? Because H4, you've already got. H4 is H3. You've already looked up H3, right? H1, you've already gotten H1 because you've analyzed the condenser. So this is it's child's play to determine QL for the evaporator. So really now you're down to answering the questions that were asked of you. First is the coefficient of performance. So in your head, you remember coefficient of performance is energy sought over the energy that costs. And so depending on your application, whether it's a refrigeration cycle, refrigerator or air conditioner, or a heat pump cycle where you're trying to heat something inside, okay, that's going to determine the coefficient of performance numerically of what you come up with. You see that you've already determined all these values on the right-hand side. Okay, determine the mass flow rate needed and the power required. So typically what I do is, well, what's the energy sought? Well, it's going to be, depending on your heat pump or your refrigeration cycle, it's one or the other of these, okay? But both of them involve M dot. So you have got, in your analysis, you've gotten QL and you've gotten QH, right? And so this is generally given. Q dot is generally a given number. It's a little rare that you're given the mass flow rate and has to find Q dot, okay? But anyway, this is the way you will find m dot because you're typically given the heat transfer rate and you've already found little q in your analysis, whether it's one or the other. Then you're able to, once you've got m dot, then you can find the power required to drive the compressor because you've already found little w of the compressor. So a lot of students get all nervous about these things, but just remember the nature of what you're doing in your analysis is you're finding little q and little w. And then ultimately, sort of at the tail end of your analysis, you're applying the mass flow rate to get the power needed to drive the compressor. That little extra credit, I'm repeating myself a little bit in a previous video. What if you're asked on a quiz or a test, or as a practicing engineer, you're interested in the quality level of state 4? What's the quality going into the evaporator? You know, is it a high quality? Is it a low quality? Well, what is it? Well, it's pretty easy to find, right? Because let's see, H4 you already know from your work. And do you see that you've already looked up H sub G, because typically that's going to be H1. You've already got that. So all you really need to do is go back and at T4 or P4, one or the other of those that you know, look up H sub F. And that's going to give you the ability to quickly calculate the quality, which is a ratio. It's H4 minus HF. It's this amount in terms of enthalpy divided by this amount going all the way across the dome, Hg minus Hf, which for our case is H1 minus Hf. Simple as that. So word to the wise, know how to do this, know how to find X4. If you're in my class, you need to find X4 because it's always a test problem. Okay, and so if you're interested in seeing how I've worked out an assigned textbook problem, problem 10.4, suggest you go to my homework solutions playlist, scroll down, and see how I work out from start to finish, including all the numbers, problem 10.4. So I hope that helps. And so do you see that the traditional cycle analysis for our refrigeration cycles, it's really a recap of previous open system work. Steady state, steady flow, one inlet, one outlet for 4 basic components that are using a phase change substance, a compressor, a condenser, heat exchanger, expansion valve, constant enthalpy in the absence of kinetic energy change, and evaporator, a heat exchanger. So the 4 basic components, and the more experience you get with it, the easier and easier this gets. Okay, I hope this set of videos helps you work through getting started with analyzing and more fully understanding refrigeration and heat pump cycles in which we're using the phase change substance, a refrigerant, whether it's R134A, ammonia, R22. You get the idea. Very powerful skill to have as a mechanical engineer when you get out into the workforce.